In this video I'd like to talk about equilibrium, and we have two types. The first is static equilibrium, and an object in static equilibrium remains at rest, so it has no velocity or acceleration. And the second type of equilibrium is dynamic equilibrium, and an object in dynamic equilibrium moves in a straight line with constant velocity. For both of these cases, the net force acting on the object is zero. We have no acceleration, so our acceleration is zero. And this is one of our conditions for an object to be in equilibrium, that the net force is equal to zero. And I would like to give you an example of this with this problem here. So we have a 500 kilogram piano being lowered into position by a crane while two people steady it with ropes pulling on either side. We're given the angles at which the two ropes are pulled and the magnitude of one of the forces. So the first thing we're going to do is we're going to draw a free body diagram for this problem. And if you bear with me, let's get an axis together here. So here is my coordinate system, and we should label the coordinate system. We'll call the horizontal direction X, the vertical direction Y. Now this piano is being lowered by a crane, so there's a tension force acting on this piano, which is upwards. So that's the tension by the crane. There is also the weight acting on the piano. Alright, one thing we should include is the piano itself. So remember, on our free body diagram, our object is just a dot centered at the origin. Alright, now there's two other forces. The first is Ellen, who is pulling to the right at an angle of 25 degrees. I'm going to zoom in here. So this angle right here is 25 degrees, and we have Bob pulling on the other side at an angle of 15 degrees. Just label this 15 degrees. Oh, it's not very clear, is it? Okay. I'm going to label a couple other things on this diagram. I'm going to draw, or at least indicate, the X and Y coordinates for each force. So, well, at least for the two forces put on by Ellen and Bob. There we go. So let's label some of these. We have the tension in the crane as it's being lowered, the weight, which is downwards. We have the force. Let's not label it a force. Let's label it as a tension with a T. The tension by Ellen. That's a vector. And we have tension in Bob's rope. Now, for Bob and Ellen's ropes, we have X and Y coordinates, components of the force. So here is the X component of the Ellen's force. That's this dotted line which goes horizontally to the right. And we also have a Y component. That's T, E, Y. We can do the same for Bob. Bob has a Y component. Bob's force has a Y component and an X component. There. So there's our free body diagram. Let's zoom back out. Okay, so we know a few things. We know, first of all, the mass of the piano. The mass of the piano was 500 kilograms, and we also know the magnitude of Bob's force. The magnitude of Bob's force is 500 newtons. Okay. So what I'm going to do now is I'm going to use Newton's second law. So Newton's second law in component form says the sum of all the x components of my forces should equal mass times acceleration. So let's write this down. So we have, you write down every force. So we have the tension in the cable, and its x component, plus the weight x component, plus Ellen's x component, plus Bob's x component. And this should equal to mass times the acceleration in the x direction, which is 0 because this object is being lowered at a constant speed. We have a similar equation for the y components. The sum of all our y components looks like the following. The y component of the crane's tension plus the y component of the weight plus the y component of Ellen's force plus the y component of Bob's force. This equals mass times acceleration in the y direction, which is 0. Now, we know a few things here. We know, first of all, that the x component of the force due to the crane is 0. It only has a y component. Same with the x component for the weight. Okay, so let's look at this first equation here. We know, well, let's write it out again. So we have T E x plus TBx should equal 0. Now TEx and TBx are related to the forces put on by Bob and Ellen, and we can write TEx as the magnitude of Ellen's force times cosine of 25 degrees. And Bob's force, its x component is negative TB times cosine of 15. And that should equal 0. Notice we know everything here except for the magnitude of Ellen's force. We're given the magnitude of Bob's force, so we can solve for the magnitude of Ellen's force. It's just TB times cosine of 15 degrees divided by cosine of 25. So TB is 500 newtons. We have cosine of 15 over cosine of 25. And finally, we get the magnitude of Ellen's force is about 533 newtons. Great. So we've answered part A of our problem. What tension must Ellen maintain in her rope to keep the piano descending vertically at constant speed? Okay, so what is the tension in the main cable supporting the piano? Well, for that we need to turn to the second equation here. We know the following. We know that the y component of the tension force in the cable is just the tension force in the cable. The weight of the y component of weight is just the weight itself, and it has a negative y component, so that's mass times the acceleration due to gravity, plus the y component of Ellen's force, which is the magnitude of Ellen's force times sine of 25, and the y component of Bob's force, which is TB sine 15, and this equals 0. I made two mistakes here. This and this should both be negative. There. So we can solve for the magnitude of the tension in the cable, and that's just equal to mg plus TE sine 25 plus TB sine 15. And we can plug in some numbers now. The mass of the piano is 500 kilograms times 9.81 meters per second squared plus 533 newtons times sine of 25 plus 500 sine, I'm running out of room, 15. Sorry, I squeezed that in. Anyways, you could verify this. You should, when you plug that in your calculator, you should find the magnitude of the tension in the cable should be about 5,260 newtons.